Hello everyone, and we're back again for part 2 of energy, and I've said up there that once you can describe energy, it can tell you all about the world. And it might be a little bit ambitious of me to say we have described energy, but at least now you should have a little bit more of an idea of how important it is, at least in understanding the world. So we're going to start looking at a few of the different types of energy from part 1, and we're going to focus on the motion-based types of energy, and we're going to start with kinetic energy, which is the energy in the motion of an object. So if an object is moving, that means it has some motion energy. And as we know, mass is very important in getting an object moving, so that means the amount of kinetic energy an object has is also connected to its mass. So kinetic energy, of course, has an equation, and this equation is slightly more complex than just a basic triangle equation. Kinetic energy of an object is equal to half of the mass times the velocity squared. So you take the mass in kilograms and you take the velocity in meters per second, and you multiply them together and then divide them by 2, and that is the kinetic energy in joules. So what are the units of kinetic energy? Take a moment to think about it. So you can see by rearranging that the units of kinetic energy match the units of work. You start off with kinetic energy equals half mv squared, the basic equation, and you transfer that into units. So the units then are kilograms times meters per second squared. And it's important to notice this is meters per second all squared. It's not the same as the units of acceleration, which means we have not just 2 seconds, but 2 meters in the expanded expression. So we have kilograms times meters times seconds. And we can condense that to have kilogram meters per second squared, which is the units of force, the Newton in its full SI form, multiplied by meters, or, as they're otherwise known, Newton meters. So I'll say again there, notice the difference between meters per second all squared and meters per second squared. They are 2 different quantities. So what this is an example of how all the different ideas of physics, and especially all the different types of energy, which is what we're talking about here, can all be reduced to the same kind of unit, in this case joules, the universal unit of energy. So here's a question about kinetic energy. If a car is traveling at 25 meters per second and it has a mass of 1340 kilograms, how much kinetic energy does it actually have at that time? And if you want an additional question, let's say the car from the first question decelerates at -2 meters per second squared for 10 seconds. What would its new kinetic energy value be? So bear in mind that it is decelerating, and that's what the negative means when you do your calculation. So next we're going to look at potential energy, and this is a little bit weird because it's energy that's stored up and isn't really visible at the moment. And one good example of this is the children's toy car, which you put on the floor and draw backwards, and then when you let it goes off on its own. So that's potential energy. When you have the car ready to release, there is potential energy in that car, and it is ready to give the car motion when you let it. So you may remember from the video before this one that there were 2 main types of mechanical potential energy. There is chemical potential energy and other types, but mechanically there is gravitational potential energy, which is energy due to an object's position relative to the Earth's gravitational field, or the moon, or some other astronomical body, Mars maybe. Or there is also elastic potential energy, which is also called strain potential energy, and this is due to the deformation of an object. So let's just give elastic potential energy a little bit longer. So let's have a look at this example. If you see here, the bottle of water has been squeezed, so its shape has changed. When it is released, it goes back to its normal shape, and this moves mass. This return to its normal shape is what moves some of the mass in the bottle, and if mass is moving, then work is being done, and that is the release of elastic potential energy. The energy was stored when you squeezed the bottle, and it was released when you allowed the bottle to return to its normal shape. And this is the same of many different types of elastic potential energy. The energy in a spring is also elastic potential energy when the spring is squeezed, or the energy of a rubber ball when it bounces off the floor or a wall, keeping most of its motion intact. So the most common form of potential energy to study is gravitational potential energy, because it's everywhere, and it comes from the fact that gravity is a constant acceleration that acts on all objects. You could get technical and talk about if you were to go to the center of the Earth, your gravity would change, but for normal everyday purposes, gravity is the same. It's 9.8 meters per second squared, a constant acceleration. And that means that if you would constantly accelerate, if there was nothing to hold you up, you must have some potential energy ready to release. So gravitational potential energy is your mass times gravity, 9.8 meters per second squared, times your height. And height is relative, so if you are standing on top of a building and suddenly you fall off, don't worry, it's just a thought experiment, then you will fall from the top of the building to the floor, and that is your height, and that is the amount of gravitational potential energy you will lose. However, somebody who is standing on the floor and sees your smashed and broken body crash down before them might fall backwards into a manhole, and they would fall into the sewer, and they would lose gravitational potential energy equal to the height of their fall going below the surface of the street. So gravitational potential energy and how it is lost depends on what height you are falling from and where it is. So the units of gravitational potential energy are the Newton meter, or again the joule. Not surprising, it is energy after all. And it's the Newton meter because mg is the force that your body feels from gravity. You don't feel it because humans are used to it. And then you multiply that by meters being the height. And as always, mass is in kilograms. Height is a distance, so that means it's in meters, and then g is just a form of acceleration, the acceleration due to gravity. So, another question for you. How much gravitational potential energy is in this 42 kilogram gymnast when she is 3 meters above the trampoline? I have no idea how much she weighs really, but if you think about this, and we're going to measure her gravitational potential energy from the trampoline, so you don't need to worry about the fact that the trampoline itself must be above the floor. So mechanical energy is what we've been discussing. This is work done by forces acting on objects, causing their motion to change. And mechanical energy is the way that we think about this in many contexts. So as we've seen, it's described by either a change in the object's kinetic energy, a change in the potential energy that's associated with the position in space, which is gravitational potential energy, or a change in the shape of the object, deformation or deformation, and that is elastic potential energy, which we're going to ignore from now on. All of the other examples we look at are going to focus on just gravitational potential energy and kinetic energy. So now we're going to focus on the work-energy relationship. So when you use force to give an object acceleration, you've done work, so you've used energy, and you've put that energy into the object. So as energy cannot be created or destroyed, there must be exactly the same amount of energy in joules going into the object as you've used, which means the force times the distance must be converted into exact amounts of other types of energy. On the next slide, we're going to look at an example of that as kinetic energy and gravitational potential energy are compared with work done. So what we're essentially doing is viewing work as an energy change, and we'll start with that as an equation. It might seem silly, but W equals a change in energy. That's because when you put work into something, the energy is going to somewhere else, and so it's not just a question of having an amount of energy stored up in some place. So if you're talking about a mechanical system, this change in energy will change the gravitational potential energy and or the kinetic energy of the object that you are interacting with. And we can say that that energy then, the work done, was a component of kinetic energy and of gravitational potential energy. And since the total energy has to remain equal, that means W must equal the sum of those two energies. So we know how to calculate both of those two energies, and here they are. Now, you might notice that we have changed the velocity and the height terms into something a little more complicated. We've changed V and H into delta V and delta H, in other words, the change. Now, this is nothing you haven't seen before, it's just the way we calculated the change in speed in the acceleration equation. Final velocity minus initial velocity, or in the case of gravitational potential energy, the final height minus the initial height. That is the change in height, just like it's the change in velocity. So we're using the same equations, but in a slightly different way. So now we can start to think about something called free fall, which is the simple effect of falling due to gravity. In free fall, that means you're going to experience a constant acceleration of 9.8 meters per second squared towards Earth. Eventually, air resistance will get to the point where it counters gravity and you will stop accelerating, and that is what's called terminal velocity, rather morbidly. But we're not going to think about the effects of air resistance. So thinking about the energy in a freefall situation is the easiest way to start because of the constant acceleration effect. Here we have a rather crude demonstration. The ball is held at a certain height, and in this scenario, this is the height at which it has the maximum gravitational potential energy, but at the moment it's supported, so it has zero kinetic energy. When the hand is removed, the kinetic energy increases as the gravitational potential energy decreases, and so it loses that gravitational potential energy as it falls, and as it falls it gets faster, gaining more kinetic energy. So just before it strikes the ground, it has the minimum gravitational potential energy it can have. We're talking about it's literally contacting the ground, but it hasn't actually impacted yet, if you like. At this point, just before it lands, it has the maximum kinetic energy that it can have during this scenario. So we're going to look at that again, only now we're going to put some numbers on it. So in this example, the mass of the ball is 2 kilograms and the height of the drop is 35 meters. The distance fallen by the ball is d, so it's important to note that that will start as 0 and its velocity is v, that's its speed. So in the first case, we're going to look at t equals 0, which is the moment at which the ball is released, but it still hasn't started moving. When t equals 0, d equals 0, as we said, and v, its velocity, is also 0. So we can calculate the gravitational potential energy. It's 2 times 9.8 times 35. So that's 2 kilograms times the gravity constant times the height of 35 meters is 686 joules. The kinetic energy at this point is 0. It's half times 2 times 0 squared, so that comes out as 0. So let's move on a second to t equals 1 second. So when t equals 1 second, the distance fallen by the ball is 4.9 meters, and its velocity is 9.8 meters per second. So the velocity is obvious because you're accelerating under gravity for 1 second. The distance is less because you didn't spend all of that second at 9.8 meters per second. So if we now calculate the gravitational potential energy, we'll see that it's 2 times 9.8 times 35 minus the 5 meters we've fallen, and that means we end up with 589.96 joules of gravitational potential energy. Now, if we consider the kinetic energy, we have a half times 2 times 9.8, the velocity squared, giving us 96 joules of energy. And those decimals add up rather nicely, and you can see if you add together those two numbers that the total amount of energy is still 686 joules. Let's not stop there though, let's move on to t equals 2. At this point the distance fallen is 19.6 meters, and it just so happens the velocity is also 19.6 meters per second at this moment. And this is quite normal as the distance gets more and more. So calculating the gravitational potential energy now, we are subtracting nearly 20 meters from the initial 35. So we've got now under half of the gravitational potential energy remaining, 301.84 joules. And you can imagine what we're going to see here if we compare that with the kinetic energy equation for 19.6 meters per second. That means we have 384 joules. Add them together, you've got 686. And then finally, after 2.5 seconds, only half a second later, the distance fallen is now 30.6 meters. And the velocity is now 24.5 meters per second. So the distance increasing faster than the velocity, as you might expect. And here, gravitational potential is 2 times 9.8 times just a few meters left. So it's only 85.75 joules, and all the rest, 600 joules, is into kinetic energy. They still add up to 686 joules, so energy has been conserved as this object falls through space. Now, we just mention again that this is a simplified example. In the real world, things such as air resistance and other effects might come into play, but these are the basic laws and the basic relationships that do hold. So that concludes our little introduction on energy, and we've only looked at some of the most basic interactions of kinetic and potential energy here. Obviously things do get a lot more complicated than that. But that's all from me for this time. See you in the next video.